there are sort of a number of goals that we want to sort of achieve when doing I/O virtualization. Basically, what we want to do is present to the virtual machine a virtual platform which looks somewhat like, at least in terms of the devices it contains, like the physical platform. It's not going to be exactly the same as the physical platform, because that's kind of the whole point of virtualization, that there is some abstraction from the underlying hardware, and you can move this virtual machine between different physical platforms without having to change the virtual platform. But it's, at least in terms of the categories of sort of devices you support, things like navigation services and wireless services and so on, these all need to sort of be present in order to make things useful to a VM running on a mobile platform. And the basic sort of things that we set out to achieve are exactly the same as those that we did with CPU virtualization. So we want to multiplex this piece of physical hardware between one or more virtual machines. We want to do it in a secure way, such that virtual machine A doesn't get to read or modify the accelerometer values of virtual machine B. We want to do this efficiently with minimal overhead and achieve maximum performance with a given hardware. We want fidelity, and Prash went into some detail about that, this idea that the virtual hardware looks a lot like the physical hardware that the guest might be expecting, at least, and it's able to perhaps not even realize it's running in a virtual environment. And portability, we want to support as many guests as possible, or as many hardware platforms. Interposability, we want to be able to have the VM be able to get in the way of the virtual machine and the hardware to be able to support cool features, things like suspend and resume. If any of you have VMware Fusion at home, or if you use a product like this, you can do things like suspend a virtual machine, turn off your computer, turn it back on, and resume exactly where you left off. Well, you can only do things like that as a result of the ability of the virtual machine monitor to actually capture the complete virtual state of the hardware. And so that's what that's why this sort of interposition property is important. And finally, and this is something that's not usually discussed in an academic context, but it's certainly important in industrial setting, is minimizing engineering costs and maximizing maintainability of your virtual machine monitor or virtualization solution. And so you can't really have all these things usually. What you do is you have an I/O device you want to virtualize, and you come up with the right point of design space to get some subset of these properties and sort of trade off one for another. So there are sort of three classes of I/O virtualization techniques that are used in general. There's device emulation, para-virtualization, and pass-through. Now, the first two of these should be familiar from Monday, because they're what we sort of do with CPU virtualization. That is, with device emulation, the idea here is we can present to the guest a virtual device realized in a software model by using sort of trap and emulate techniques. That is, the VMM uses privileged hardware to be able to set up traps on the guest's accesses to I/O registers or memory mapped regions, and it's able to respond to these traps, present something which the results back to the guest which make you believe it's accessing a real hardware device. And so that's the basis of device emulation. Para-virtualization is sort of similar, but instead of actually using a hardware-defined interface, we can use a much higher level sort of API, one which is better suited towards virtualization and allows sort of higher levels of performance and simplifications to the virtualization solution. And the final one is pass-through, which is something which we haven't seen so far, because that doesn't really apply in the case of CPU virtualization, but it's the idea that you can assign to a virtual machine exclusive access to a specific physical device, and actually not have to do any direct virtualization of that device. And that's actually, it's sort of problematic, as we'll see, at least in many cases, because you lose things like interposability and so on. But it does enable sort of high degrees of performance because you have this direct relationship between the VM and device. So in the next few slides, I'm just going to go through these again, just using a running example of to sort of illustrate the concept. So here we have device emulation, and you can see at the sort of the bottom there, inside the hypervisor lives this device model, which is a sort of a software model of this thing we call, let's say, an Acme UART. Up above that is the guest operating system, and we have your device driver, which is capable of speaking to the Acme UART, and they communicate, as you do with a UART, you know, banging out bytes on a FIFO, reading from a status register, and so on. Now, the hypervisor will just be, you know, emulating this Acme UART device, may not be doing anything with it, but in order to actually have some useful real-world consequences of the virtual machine's actions, you probably actually want to communicate with a physical UART or some other kind of backend. And in this case, you might be speaking to a completely different type of UART, let's say a foobar UART, and it might be writing out in a different sequence and using different sets of registers and so on. Now, this is sort of a very attractive solution because you can do things like leverage the fact that the existing guest operating system already has support for speaking to Acme UARTs. You don't have to modify the guest operating system at all to be able to actually support its use of these hardware devices. It allows you to interpose. It's portable in terms of the guests that you can support. It does come, though, at some costs, particular emulation overhead. Each of these traps that occur require that you enter the virtual machine monitor, context switch the hardware, process the exception, you know, update the device model, and then return back to the guest. And this can be quite sort of an expensive thing when the trap frequency is high, and you can see that sort of a hardware-defined interface like the one here might make this high, because in the case of the UART, it might be sending it across one byte at a time, and we have to trap for each byte that's being pushed out. So the other sort of downside of this approach is it comes at sort of some VMM implementation cost, and this comes back to the engineering cost that I mentioned earlier. You have to build a device model for some hardware which already exists, which may, you know, when it was originally created, have corresponded to some hundreds of thousands of lines of VHDL or Verilog or some hardware design language. You now need to realize this in the software. And in fact, you need to do sort of work backwards from specifications and build these models in the virtual machine monitor, which can be, you know, quite complex. For a UART, it's pretty straightforward. For something like, let's say, like a graphics accelerator, that's certainly not the case. Okay, so power virtualization, as I mentioned before, we changed the sort of interface here. So rather than speaking the Acme UART sort of set of registers and commands, the guest now is actually modified to use this to speak a custom protocol with the hypervisor, and we insert into it this power virtualized UART driver, and you can see here, rather than sending out individual bytes, what we might have instead is a sort of a ring buffer shared between the guest and the virtual machine monitor, and you can much more efficiently transfer data in this way and minimize the sort of virtualization overhead. So this obviously enables higher performance. It might simplify the VMM because we don't need to support all the features that a real piece of hardware might support just because the guest driver happens to be using them. Still allows interposition. But it comes at this sort of cost, and then this is where the downside is, of having to modify the guest operating system. So you have to go in there and actually modify, write sort of a custom device driver, and that's not great in general. In the case of MVP, in fact, this is our preferred solution. In fact, most of our virtual platform in our hypervisor is para-virtualized. And this is largely a case because in the mobile setting, there are very few guest operating systems you do need to support. You don't have end users loading up operating systems from CD-ROMs. This doesn't happen. Phones ship with OSs. And in fact, today, there's been a lot of consolidation in this space. And in fact, really just two sort of main operating systems that people seem to care about, sort of Linux, iOS, and I mean, maybe Windows, but there's been a huge sort of consolidation, even just the last year, in terms of the platforms that you need to support here. So the final technique, and we won't be talking too much about this today, but just for completeness, I've thrown it in here, is pass-through. And this is something that enables a very high degree of performance because you're assigning directly to the guest a physical UART, and it can speak directly with it without any need for the hypervisor to be involved, at least in after a setup and before teardown. It allows you to achieve essentially a huge simplification as well to the virtual machine monitor, because there's no need for you to actually write any kind of device model for the device that you're targeting. But it comes with sort of some significant downsides. To start with, interposition is very challenging. It's either impossible or perhaps possible if you use a hybrid of some of these techniques, which are sort of presented as pure techniques, but they're not. You can use sort of combinations of them. And it also requires some sort of somewhat sophisticated hardware to support in order to do safely. Most non-trivial devices have DMA engines present on them, and if you just assign these devices directly to a virtual machine and allow the virtual machine to communicate directly, you could easily violate the virtualization abstraction of memory and the security of the platform. And so you need a new type of MMU, different than the one that's present in the CPU, called an IO MMU, to enable the devices to be safely isolated when doing sort of pass-through virtualization of devices. So that's all that I wanted to sort of talk about in terms of virtualization techniques. Now I'm just going to go into sort of what this I/O virtualization stack looks like and what the different components look like. And in particular, I'm going to focus on how they look like on the MVP hypervisor. Now, before doing that, though, we need to make sort of a slight diversion and look at sort of hypervisor architecture, and because this has sort of some implications for what the I/O virtualization stack looks like. So there are sort of two main categories of hypervisor architectures. There's the bare metal or type 1 hypervisors and hosted hypervisors. Now, bare metal hypervisors behave a lot like you might expect hypervisors to behave. They run directly above the underlying hardware. There's no layer of software between them and the hardware, and above them runs all the guest virtual machines. Inside the VMM, you also have present all the device drivers that are necessary to speak directly to the physical hardware. And so that's certainly one approach, which is which is ideally suited for things like server use cases where you really want to minimize the amount of overhead present in the system, and you also want a very sort of precise control over things like scheduling and resource management inside the hypervisor, because you're sharing this piece of hardware between these workloads with sort of competing interests. This is sort of the preferred architecture in things like VMware ESX, Xen, Microsoft's Hyper-V, and so on. Now, when it comes to client virtualization, that is when you're virtualizing things like your laptop or your mobile phone, things are a little different. And there's another model which has significant advantages in this space, and that's sort of the hosted or type 2 hypervisor architecture. And here what you have is you have on your device already an existing operating system, which we call the host OS. So you have something like Mac OS or Android already present on your phone. You've been using it for a while. And then later, you want to sort of launch a virtual machine or install some virtualization software. And so in this approach, the VMM, it comes a bit later to the game. It doesn't run directly, at least initially, on the hardware. It's installed on the host operating system, a lot like a host application might be. And it appears to you on the host like any other host application. There's an icon there. And when you tap on this icon, what happens is the VMM is launched. And the VMM, as we sort of saw on Monday, needs to be privileged. It's not just a normal application which can run directly in user mode on the host operating system, but it's capable of actually achieving these privileges that are required as a result of other components that might be present, including a kernel module, which you are required to support it. And this is sort of very common approach in client virtualization. You see this in like VMware Workstation and Fusion and Parallels Desktop and KVM and so on. And it's in fact what we use in the MVP hypervisor. And I'll sort of talk a bit more about the sort of advantages of this model with respect to MVP in the next few slides. So this slide sort of presents the MVP system architecture. It's similar to the previous slide in how things are laid out. At the sort of, on the right-hand side, you have the sort of the guest virtual machine and the VMM, and on the left you have the host applications and middleware, and then the actual host kernel. So all the things in dark green are what are present on the phone before we place our mobile hypervisor there, and then things in turquoise and light yellow, these are sort of come later and sort of supports the virtual machine monitor. Now, this is sort of a great model for like our particular use case, which Price spoke about on Monday, and that's this idea that you have a dual-use phone and you're using it for both home use and sort of your work purposes. And so you already have your phone, which you've gone down to the store and purchased, and you just want to use this to play Angry Birds or access Facebook. And at some point, you want to actually access corporate network resources in your work email. Well, you can, rather than having to wipe things or install a virtualization layer there or something like that, you just install the VMM almost like an application and the guest virtual machine on top of that, and you can actually access these resources. So other sort of key advantages of this kind of architecture, perhaps one of the most important one is the ability to tackle SoC diversity. So I mentioned before, phones are organized as system on chips, at least, and particularly the application SoC is what we're interested in. There's not just a single standard for these. It's not like in the, let's say, PC space where you have Intel and AMD and they basically set a roughly compatible standard architecture. The cores are very well standardized by ARM, but the actual devices around them, they're actually assembled, and these SoCs are put together by silicon vendors like TI and Qualcomm and Samsung and NVIDIA. And these companies essentially take various bits of IP and build their best-of-breed SoCs. So they have things that they'll take a UART from one source and a graphics accelerator from another and assemble them as they see fit. And there's limited standardization here. What this means is you sort of get this nightmare that occurs for system software implementers who have to support these chips because they need to support this a huge number of chips, each with different sets of hardware and different platform configurations. So with a hosted sort of hypervisor architecture, you already have a host operating system there that knows how to talk to the hardware. It's got device drivers already supplied which are capable of addressing this hardware. So there's no need for the virtual machine monitor to actually have these device drivers. Instead, it can make use of the services provided by the host kernel to speak to the physical hardware present on the platform. And so that's one of the key advantages here. You can sort of leverage the existing host device driver support. It's also great in the mobile space because it reduces time to market, which again is probably a concern which is more unique in the mobile space, which is unique in the mobile space. And particularly in mobiles, you have these sort of lengthy development cycles. It's well over a year usually between the conceptualization of a phone and when it actually arrives in the store, and it needs to be assembled out of various bits and pieces. It's better if you can sort of avoid impacting or having too tight a coupling with this development cycle, and using a hosted hypervisor enables you to place the hypervisor on the device almost just before it ships, rather than having to be there right from the beginning of the development of the phone software stack. Another key advantage is it sort of eliminates the need to do any virtualization of the applications running in your home profile. So let's say you don't need a graphics accelerator in the work VM. There's no need to actually do I/O virtualization of the graphics accelerator. Instead, you can just leave that unvirtualized, allow the home profile to use it, so you can continue to run Angry Birds there, and you can simplify sort of the virtualization solution as a result. So, in a hosted hypervisor, the I/O stack looks a bit like the following. We usually divide it into two parts. There's the front end and the back end. So the front end we've spoken quite a bit about already. This is the interface between the guest OS and the VMM, and that's on the right-hand side here. You can see the top there, the guest OS and the virtual machine monitor. And then that communicates across to something called a backend, which is how the actual virtual device semantics are realized with the physical hardware. And this is typically a host user application, which is sort of running there on behalf of the VMM, and allows the VMM to make use of the services of the host kernel and be able to do things like, writing characters out of the serial port, or displaying something to the frame buffer, or accessing the GPS. So on the front end, there's sort of a few design choices. We've already talked about the virtualization techniques, but there's also sort of like what level of the stack in the guest you might apply these at. There's device simulation, which is clearly sort of in between the operating system and the virtualization layer. There's device level para-virtualization a bit above that. That's sort of those are the two things we've talked about so far. There's also para-virtualization further up the stack, which we actually make use of an MVP, and is also a viable solution depending upon the actual device and what support there is in the mobile OS and middleware for virtualizing at this level. But you could, rather than actually having to virtualize a physical device or provide a virtual device which looks something like a physical device, you can actually just replace libraries in the guest operating system, have them call across to the host and make use of similar libraries there. Now at the back end, there's as I mentioned, there's usually what you do is you have this host application which is running sort of on behalf of the VMM, making use of kernel services, and it uses standard system libraries and the system call interface. So, for example, on a Unix-like operating system, the backend for the UART might not be speaking to a physical UART directly. Instead, it might just be writing A out to dev ttys0 or something like that. That's the typical way these things are done. And this is great. It's portable, simple, largely language independent. You can use sort of any implementation language that you feel like for the backend. In fact, in MVP, many of our device backends are written in Java because that's sort of the standard language on the Android platform. But it does come with just one slight trade-off in that there's a little bit of additional sort of latency, overhead, and lack of control of schedulability here. And it's not an issue for almost all devices, but for some devices, like let's say virtual timers, it can be a bit of an issue. And instead, sometimes you might choose to implement your device backend directly in the host kernel via the kernel module that exists, and that's another sort of viable approach. The main downsides of that is you introduce sort of close coupling with the kernel, which its internal APIs are not always very stable. Linux's APIs change between different minor versions, for example, whereas the POSIX interface has been stable probably for decades now.